welcome to that web session here, and thanks for joining. And as Eric mentioned already, I would like to talk a little bit about fan-out wafer and panel level packaging. And I will start with an introduction and in general about fan-out packaging, and maybe also why we offer a session on fan-out if we say we would like to talk about advanced substrates or beyond PCB. Why is fan-out also a topic in that area here? I have some nice overviews about wafer level packaging, what we are doing here, maybe what technologies, what approaches we are developing, give then or move over to panel level packaging and look a bit to the past and maybe what is ongoing at the moment. As I think we are facing maybe a second wave of that topic here. I have 2 slides at the end, a bit on cost and environmental modeling, because we also have a nice example here for fan-out, wafer and panel. And of course, I will finish with a quick summary and outlook. So let's start with the introduction. And this is also a bit why maybe fan-out is interesting when we are discussing substrate or beyond PCB technologies. So of course, first of all, fan-out is more a packaging approach and not only a substrate. But in general, I think we see more integration on the substrate, more functionality. And even if fan-out approach is a substrate-less package, I think we will see that it also has different flavors, not only as a package, but maybe also giving very smart solutions for next generation applications. Chiplet, I think, is one of the hot topics at the moment. And you see a little bit how the world is structured if you discuss about 2D and 2.5D architectures, of course, also 3D. And as Eric already shown, I think we will also cover some of the other topics here, especially on the organic interposers, on glass core substrates here. I would now pick up that fan-out topic here. We'll give at least some comments on maybe bridge technologies, which maybe we will see more in future. But you see, we do have a lot of options as interposer for advanced packaging. Of course, we have also silicon here, and we have the real 3D integration. And I think what we see at the moment is also a little bit how to extend maybe the organic solutions. And just only having, of course, we see a lot of progress in organic interposers, substrate technology. We see glass core substrates, which in the end also is maybe an extension of organic interposers, because we use a glass core with organic ABF layers as RDL layers on both sides. So there is also a lot of technology from pure organic interposers included, and we have fan-out also as an organic solution, maybe combined with a bridge for very local high density routing. And of course, the chiplet is driving us, and we see, Eric already teased that a little bit, large HPC modules, AI modules, chiplet topic with very large packages, module sizes is also driving at the moment these approaches here. And here also again, the panel level packaging comes into the game again. I think most of you have seen that slide before. So I think fan-out has a lot of different flavors. This is not all of them. It's not all companies involved here. You see, I think in most of the approaches, we have worked on wafer and panel formats, and you will see a lot today on that mold first face down approach. I like that quite a lot because it's a very nice approach for heterogeneous integration, because it's very easy to integrate different components, even from different suppliers with different PET metallization and so on. I would think most of you know the process. You have a carrier with a release tape, you place chips face down on that, you do overmolding in a large wafer or panel format. you have a temperature step for carrier release, and then you can build up an RDL on top. So, and you already see there is no interposer involved, or the RDL in the end is the routing layer, is the interposer here. And of course, there is the face up option, where you also place bare dies face up, in this case, on an intermediate carrier. In this case, you need chip preparation, you need stud bump, for example, or a bump on top of it. You do overmolding, you need to back grind into that bump you have on the chip, and then you can add the RDL again on top of it. Means you need chip preparation, means you need wafer access, at least here for the bumping. And I think you need be careful also with the chip thicknesses, and even if you now like to embed maybe also passive components or other modules, that is not so easy as if you do it for the face down version. The last option maybe we should look at this at the moment is RDL first. I think it was called in the beginning more or less. I think we see more and more also RDL interposer for that. And in the end, it is an advanced flip chip on flex, honestly, because you use a carrier, you build up an RDL on this, and then you do flip chip assembly on top of it, overmolding, underfilling, maybe in one step, debonding from the carrier. Usually you need then some cleaning and etching steps, and balling at the end. And it's interesting if you see also how technologies evolved and maybe some pros and cons, especially on yield and cost-wise. Of course, this is all embedding processes. That means you have the chip, do the mold embedding first, and then add the RDL. Where on the other hand, here you have the RDL first. Maybe you can even test the RDL. So you have maybe a known good RDL and place the die on top of it and do the overmolding. So yield-wise, maybe it might be a bit better, especially if you have an expensive die, to go maybe for a kind of RDL first, RDL interposer approach. But have a look later to that. If we look to what we are doing at the institutes here, so you already see or maybe know that we have these two worlds. So we have the wafer level technology, where we are coming from fan-in RDL processing, from bumping, from TSV technology. So this is really what we have, and also long-term experience here on RDL technology. And on the other hand, we had built up during the last decade or even longer panel level technologies. You will see we have an own panel line in-house, so we can really work on large formats here, and we're really working also to bringing that to fine lines, to multi-layer, and really to a lot of embedding, integrating technologies here. As mentioned, so that is all what we have in-house, especially here in Berlin. When we work on fan-out wafer level, we do that here all in Berlin. This is mostly RDL last. For RDL first, we also have projects running to us together with our colleagues in Dresden. Then we are working mainly on 300 millimeter. For RDL last, most of the time, if we do process developments, we do that on 200 millimeter formats. But in the end, this is something we can scale to 300 millimeter, or then in the next step to panel level. And this is what we all have in-house. So we also have the full process, full line here in Berlin, in this case, beginning from assembly, measurement, compression molding, debonding, coating for spray coating or lamination. Laser drilling is a nice option for some materials, for some mold approaches. And of course, we also have all the RDL processing. And maybe what I also have to mention for the lithography, at least on panel level, we have decided to go for laser direct imaging, so a writing technology, which also allows us to do some adaptation. This is maybe one of the challenges also when moving to panel. We're working with organic materials, So that is different as if you have maybe a silicon or glass substrate, which is very stable. If you have an organic substrate, there is always some shrinkage, some warpage, and so on. And there it helps really that maybe we can adapt some structuring also concerning the RDL. There is a lot of equipment there. I think we also start, or Germany will hopefully also start with the European Chips Act in November now. And I think there is also a couple of equipment on panel, but also a lot on wafer size, which will further enhance these two lines here shown. Yeah, let's start with wafer level fan-out packaging. I would like to show one slide. I think we're doing application-wise a lot of high-frequency applications because there is fan-out a very nice approach because in this case, no substrates and very short interconnects because you only have that metallized RDL line from chip to chip, for example, and the connection is a microwire. So there is no bump, no solder interconnect included in the package in that, and this is really nice here for RF applications. And you see a bit the different topics we are working on at the moment. Of course, it is multi-layer, and multi-layer in this case is not 2 or 3 layers. It might be even 4 layers or even more. I think you easily see the wish for more layers if you discuss with designers, especially also here in the RF area. One challenge, of course, here is warpage. If you stack one layer on top of the other layer only on one side, you can imagine that you have to somehow deal also with warpage in this case. Multiple die integration, of course, we have seen before. This is one example here where we had one package with 3 dies included and 2-layer routings here. One topic we are really having different projects running is on not only silicon integration, but 3-5 components, especially here on GaN and gas. And this has quite different challenges because we have very thin components, very brittle because it's maybe GaN on SiC, for example. And we have gold metallization, gold backside metallization, but also gold frontside metallization for the pads to connect the RDL. And in addition, of course, there might be a lot of heat generation, so you have to carefully work on concepts, how to get rid of the heat, so you need heat set embedding and so on. But this is maybe one very nice topic also where we have built already packages with gas and GaN dies, with GaN and silicon dies, and maybe even add in this case also passive components as a component itself in the package. And finally, we also see, and this is also especially for RF, but also for other applications, that we need PDKs. So we need maybe clear PDKs for co-design of chip and package. I think for the next generation of packages here, you can't design the chip without considering the package. So also here we need really better PDKs, test structures we do for evaluation to can better describe the package. I think this is also one topic definitely for the future. Yeah, this is the example where we have gas and a GaN die with an embedded heatsink we have used here. You see that works quite nice. You see very thin components. In this case, also the component itself has through wires to bring the backside interconnect to the front side. That helps for the fan-out integration because we don't need a zoom package here in this case. But this also worked very nice. You see a bit how the heatsink is attached to the backside, and then we can more or less follow the standard RDL last process flow. So we have even can attach the heatsink on that intermediate carrier before we go to molding, and then at the end grinding the package to open the heatsink backside so that that could be attached also to an cooler or the next level heatsink here. So, and we have a standard SMD package which allows standard pick and place reflow soldering on board. This is a different RF example here. In this case, it is an or it was an RDF first package. So you can maybe see that here. So we had the IC was placed on an RDL on an intermediate carrier soldered here. So here we had micro pillars, copper pillars assembled, and we had large SUMO vias plated together with the RDL that were roughly 200 micrometer in height. And then we have applied directly on the mold first shielding layer, have overmolded a second time to integrate the antenna directly on top of it. Again, direct metallized on the epoxy mold compound. And we used laser drilling for SUMOLD wires for the second mold layer down to these SUMOLD vias. In the end, that was an antenna and package for 5G applications. And you see a little bit, we first had made dummy samples to evaluate technologies. If you look to this one, if you do overmolding in the second step, in the end, you also have to align with your antenna, with your mold wires to the first layer. So you need strategies how to align swirl black mold layer to a lower layer. So that worked quite fine. We have worked on laser drilling to stop on that shielding layer here and also to metallize that blind wire. And so we had done that for different antenna structures. And at the end, we have built the final model you see here. And in this case, the IC is much smaller than the package, but we have 4 patch antennas on the backside. And it worked quite well. So you see also a bit on the measurement results here, so that the simulation fits quite well to the measurement results on the real samples in the end. So there is also more functionality to the package, to the mold here, by adding a shielding layer, by adding antenna layers directly on top, and using also the mold, the SUMOD technologies. So this is not far away, and in the end, we're using also the same equipment and technologies we use for our PCB and embedding technologies. So if you join the next sessions, you will see that we really rely on the same equipment and same line in this case for the panel level packaging. We have went to a next step and said, okay, maybe we don't want only a 2D antenna or on a flat surface. Maybe we would like to have a 3D shaped antenna that helps us for opening the detection range. In this application, it is for a 79 gigahertz MIMO radar. And so we have developed, first of all, the possibilities for 3D molding and compression molding. This is typically flat, large area molding, but you can modify to also have that 3D shape. And we have developed how we can do direct metallized on these 3D shapes, also over these edges and corners here, and having antennas also on that 3D shapes. And again, so you need the shielding, the ground layer, and the antenna. So also, as shown in the last example, you need a double molding step again here. So, and this is also, you need quite good alignment between the first and the second mold to have that 2-layer molding here. And you see a cross section, and it is not perfectly aligned. So you see that there's 130 micrometer to 170 micrometers. So that is a bit offset on 20 micrometers. But this is really a question on tooling cost. I think this is really with a more advanced or precise tooling, you can also overcome this alignment. And again, you see we have worked on blind vias to connect that antenna layer to the ground layer, but also with larger SUMOLD wires to the backside here. of the package in the end. Okay, and also to pick up a little bit more the topic on direct metallization on molds, there is also an option to have an extreme cheap package, because it was for a small chip package, for a MOSFET package, so where you need front and back sides electrical connection of the component itself, and typically this is done in a lead frame package. And here the idea was, okay, we do that in a molded package with direct metallization, is maybe not fully fan out, and maybe to have it as cheap as possible, also have the transfer to a large panel. And you see a little bit how that worked, and maybe you also can recognize, so it was a 3-step molding process. So we used the chips. In this case, it was overmolded the first time. In this case, the partner said they have so many stud bumping machine, they do a copper stud bump and not a plated bump, but I think for the overall process flow that doesn't matter. So you overmolded that here for a first time, did a grinding step so that you could also add the metallization on that top side here. And you of course need then to bring the backside contact to the front side. So that also was done by direct metallization and a laser drilled blind wire to that first metallization layer. And then of course it had to be isolated again. So you do an backside overmolding to have that isolated. And then of course you have also needed the front side metallization step and a back grinding step to access these connecting pads here later. So this gives you also an idea what is possible. So also no substrate included, even no real RDL, no dielectric material, a whole package only with mold and direct metallized copper. Could be a very cheap solution, especially if you go to a large format. One more example is what we have done. And this is just to give you an idea on the possibilities, maybe also to combine different options from that first process flow. So that was a universal sensor platform. And the idea was that you have a core with a system on chip, which is your logic, your chip who can control and calculate and so on. And this is quite universal. So you have the possibilities to add different sensor system in a second level on top of it. And so this again was as an approach in RDL first. So where we had built the SOC, there was a lot of IPDs needed also. In this case here, we again had these plated SUMOLD wires. And then it is an RDL last on top of it. So we had, of course, grinded to have access to the SUMOLD wires. And then we have applied an RDL on top of it and had the possibilities to place different sensors on top of it. And a little bit the idea was so that core package level is fixed, and then you can maybe modify just the second level here, adapted to the needs of maybe different sensor applications. And that could be even if you maybe go to an laser direct imaging, it could be quite easy to change also the RDL here, depending on the customer. And just some images. So we built that, we have tested them. You see that is a top view photo, quite nice with 4 sensors. You see the routing is not too dense, but we also had SMDs soldered on top of it. And if you look to the cross section, we have here the SOC, we have the IPDs. And you already get an idea of one of the challenges in general we face, because you see that the warpage is nothing you can neglect here, and this is definitely one of the challenges where we have to still work on it to overcome that and minimize that. You get a bit an idea on that RDL first, on the RDL. So we have caterpillars soldered on that RDL first here. And of course, we have to do a molded, or in this case, we have done a molded underfill. And also nice to give you a bit the dimensions here of the solder ball for the board level assembly, the sumud wire, and the core package itself. And in the end, it's a little bit the idea what we see at the moment on a, maybe not for that universal sensor package, but also as an extension of what we see, what is possible in these organic packaging. And chiplet and all these HPC is I'm pretty sure one driver here is that we have bridge solutions. And I'm pretty sure that we will see more of these bridge approaches. And in the end, the bridge means we have a high density routing element for local routing. So that could be between the CPU chip and the memory, but that could be also between two chiplets here. And we have a bridge, which could be silicon, which could be glass, could be with silicon, through glass vias, could be also without. And this is just one idea how such a package could look like. So, and you see that is quite similar what you have seen before with that universal sensor package. So you have one component embedded here. And in the end, this is a substrate because this is nothing more than a routing layer, maybe with a bridge inside, high density routing locally. And then you did then you do the assembly on top of it of the chiplets of the components, also with the caterpillars, for example. But then you would also go to a second molding step and maybe back grinding to get access to the chip backside for heat removal. This is not so new, the idea of bridges. You know maybe that Intel has that EMAP technology that is a bridge in a printed circuit board. And this also makes maybe approaches or extension of the organic and not moving into silicon interposer technology, for example. This and is maybe also a little bit the cliffhanger to the next, if you're looking a bit more into panel level packaging, is of course also an approach which you can scale from wafer to panel. And maybe this is one of the big also advantages for this fan-out approaches. I think we saw a first wave or first developments in panel level packaging, of course, in saving cost. And if you step back a bit to that technologies, there is not a really reason to do that on a round shape. The only reason is that we have established processes and materials for wafer processing. But if you look a bit closer, and everybody who has seen a wafer knows that it's not the best idea to place something rectangular on a round shape because you lose a lot of area, and as larger your chips, your packages get, as more area you lose on the wafer. So it's much more effective to place it on a rectangular, on a panel, and you can do a lot of calculations. And I think for most of the combinations of package sizes and panel sizes, you'll be much more effective on a panel. And of course, this is one reason why it is cost effective, because you have a much higher area utilization, you have less waste of materials and unused area you have to process. And of course, in addition, you do parallel processing of more parts for the most process steps. So, and still, if you move from fan-out wafer to panel level packaging, the package in the end, the singulated, not really shows if it was manufactured on wafer or panel. So you still have all the advantages from fan-out wafer level package if you move to panels. And we also have seen some interesting movements. If you have followed this during the last years, there were some new players, maybe from other technologies, especially from displays and solar panels, who were interested in move into panel level packaging because they have equipment and also could use it, and we're looking for new opportunities, but to use with all these lines which are already available. And we also have worked quite a lot on that topic. So we had 2 industry consortia, both were running 2 years each, and we've worked on the basic technology developments. And in the second phase, we have really looked a bit more to the limits in RDL, in VIR, in really die shift and warpage topics here, and also have looked into these cost structures and also in that environmental calculations. I can show that, or will show that at the end quickly. But it really never fully, or it was never really flying. There was a lot of investment. I think there was capacity built in Taiwan, in the Philippines, and Korea, and but it never really was very successful. And of course, there is high investment cost, and you need a really high volume to fill that line. This is a bit, if you have a panel line, you have huge capacities for manufacturing packages. We still see, I would say, challenges in warpage, in die shifting, in RDL shrinkage, in handling. There is no really panel standard. I think SEMI tried a little bit, and there are some preferred formats, but in the end, if you look to some overviews, it's really funny what different sizes people use for panel manufacturing. And then, of course, there's always the question, do we need the same challenges or RDL features we do on wafer level? Are there maybe special applications which may fit better on the panel because they're a bit relaxed in lines and spaces, layer numbers, and so on? In the end, it's also not clear what is a sweet spot. So it really never was a big success. But what we are seeing now is that in the last, I don't know, 2 years, we see a lot of new packages coming from these high performance computing for AI, very large package sizes, actually in the beginning 5x5, 10x10. Maybe some of you have seen that Tesla Dojo training tile, which was more 20x20 or something in that direction. So very huge packages, let's say it this way, there's very huge interposers needed. We see the chiplet topic, where we also expect to have larger package sizes. You see that it was TechSearch estimated here for some applications. And maybe there's also a little bit the expectation that if that Glasgow topics is getting more mature, that maybe there's also panel level processing, that this is maybe also some synergies between both approaches here. And we already seen first chiplet packages here. This is one example from AMD, where at least it is no longer in silicon interposer or very advanced organic interposer. We already see here that fan-out interposers are introduced. And in the end, this is an RDL first package type. And in this case, and this is also what at least Samsung has shown on their roadmap, if there is at a certain package size, maybe it's time to switch from wafer to panel. And you already see here is a bit that maybe you move from a silicon interposer to a bridge and RDL solution as shown before. My opinion is as long as you can stay in organic, you will stay in organic. We know also from discussions with automotive industry that they don't want to go into silicon interposer technology. So that is all also maybe a part of that discussion. And also if you look, if the package is much larger than an reticle for a stepper technology, then also all these writing laser direct imaging technology is getting much more attractive because you don't have to stitch reticles. You really can, in the end, write a full panel with one structure at the end. And this is a little bit, I think, where we see at the moment that there might be a second wave of panel level packaging. You see there was a lot of announcement also in the news here, and maybe you also have seen that even TSMC has invested in a mini panel line. So let's see what we will see in the near future here on that topic here. But yeah, so people get back to that. There is a lot of developments done already. Of course, I think there is still space for a lot of optimization, and you see a couple of topics here. Warpage again is really, I think, for a lot of the advanced packaging technologies and an issue here. It's a funny mixture of materials with different properties, CTEs, different process temperatures, and so that causes some stress popping up in warpage. We do that materials do shrink and have CTE mismatch, so that's where white dies maybe are shifting in an RDL last, but also for RDL first, maybe some RDL shifting, shrinkage can happen. Still, how fine line we must be on the large panel and what is the cost effective, and also driven by the different applications. I think we need maybe also for RDL wise have to further develop also on the panel, especially on the RF stacking of wires is highly required. We cannot only shrink the lines and spaces. Of course, we have to shrink also the wires, otherwise it does not make sense. And so you see extreme multi-layer stacking. So there is also a lot of topics for the RDL to further develop. Some final words for cost and environmental modeling. As said in the beginning, one driver in the beginning for panel level was cost. And we have looked a little bit into also the cost structure. Of course, we don't have a full manufacturing line, so it's a prototyping line, I think, but it helps to understand the cost structures. And you see one big part of the cost structure is definitely the material. So that's highly developed materials for the mold compound, but also for the dielectric, for the RDL. So that has really a big impact here on the overall cost structure. And if you now remember, you have a much better area utilization on the panel. That also means you have much less waste and unused EMC. That's the same for the dielectric material and so on. But even out of that, you get an additional cost advantage because you have also a higher utilization of the materials you use, and not cut away or dice away at the end, because you have a quite worse area utilization here. And this also is a little bit on the CO2 footprint. Of course, if I have less waste, then we have a higher efficiency also material-wise, and that also means CO2-wise. And but it's also required that we need a high yield. And this also has, of course, impact on the cost structure, but this, of course, has also an impact on the CO2 footprint of my package. And what you can see here a little bit is that the front end has a much higher footprint than the back-end processing here. But if you go to these embedding processes, maybe where you have the chip first and add the RDL on top of it. That means if you have an RDL failure, you not only lose the RDL, but also the chip embedded. And this is a cost issue, but in this case, it's also an environmental issue. That might be a little bit better for that RDL first, RDL interposer, because here maybe you can test the RDL before you place a die. That is still not a guarantee that you have 100% yield, but this is what you always should keep in mind if you discuss also all these embedding technologies, that losing the chip yield-wise is really a worst case for the CO2 footprint here. And with that, I would like to finish a little bit. I've shown a couple of examples for fan-out wafer level packaging, and that has significant package miniaturization potential. It's substrate-less. Even I think it is also a kind of interposer package approach here. They have very low thermal resistance, quite high performance due to short interconnects, and even to do integration of antennas and shielding and maybe even passive structure we have done in one of the projects. So you can also think about filter structures, for example. And yeah, multiple chips, heterogeneous integration, and the scaling to panel can help also to lower cost, and maybe also having new higher manufacturing capabilities for AI, HPC, chiplet applications. But also, as mentioned, we need a high yield cost-wise, but also for the CO2 consumption. And not a big outlook, but a look to the roadmap. And that also is a little bit what I try to emphasize. So it's not only a chip package, and it's even not a multiple chip package. Side by side stacking, of course, that is all possible. But we really see more the trend for more functionality. I think I showed a little bit on the antenna and package, shielding. We see interesting combinations with double-sided, multi-layer, and all these things. I think we will see much more functional integration, and I think really heterogeneous system integration in future. Okay, thanks for your attention. And I think we have a little bit time left also for questions.